Hello, everyone, and thank you all for joining us. Today's webinar is Polyketone, a next generation sustainable nylon alternative, and is presented by Avient Corporation. Your presenters today are Dr. John Swanson and Jeremy Gray. Dr. John Swanson is a polymer scientist with 13 years of research experience. He joined Avient in 2016 as a pioneering member of their Technology Leadership Development Program and is currently supporting the specialty engineered materials business as technology manager. Jeremy Gray is an application development and technical service engineer for specialty engineered materials at Avient. He holds a degree in plastic engineering and technology from Penn State Behrend. My name is Carly Sheeter with UL, and I'll be moderating today's webinar. Please send us your questions by typing them in the question tab located on your screen. Our panelists will answer them at the end of the presentation. We are recording today's event, and we will send you a link by email when it has been posted to ulprospector.com. Now I'd like to turn the presentation over to Dr. John Swanson. Would you like to begin?
Yes, thank you, Carly. All right, well, thank you, Carly, for that kind introduction. I want to thank everyone on the webinar this morning. I appreciate you coming to learn more about Polyketone, and Jeremy and I are excited to present our information to you. As Carly mentioned, my name is John Swanson. I've been with Avient for a little bit over 5 years now, and my background is primarily in polymer science and polymer chemistry. So I'm going to be taking over the first section of this webinar, talking more about the market dynamics and polyketone material overview, generally about the performance characteristics of the resin and the lower carbon footprint of the material, and how it compares to other engineering thermoplastics, in particular, different families of nylons. Then I'm going to hand the reins over to Jeremy, and we're going to discuss more of the applications and working with polyketone before leaving you with a highlight of some of the solutions at Avient. As Carly mentioned, you can type any questions that you have in the chat box, and we will answer them at the end of the webinar. So let's talk about why you're all mostly probably here, and that is the current market dynamics affecting the engineering thermoplastics market right now. And that's going to be primarily supply chain constraints and sustainability drives. Now, over the last 2 years, nylon 6,6 in particular has been in extremely short supply. And this is due to a mixture of bottlenecks in production chains and high demand in the automotive sector that's left many customers struggling to find this material. Now, if you've only been in the thermoplastics market for a year or two, this might be surprising, but of course, the nylon market saw a similar constraint during 2018 and 2019. So this is more of a cyclical happening, and our current situation of material lack of availability is not predicted to get better anytime soon. Additionally, customers are growing more and more conscious of their consumption habits. They're placing increased value on brands with responsible practices and products that align with such ideals. And companies, in turn, are responding by looking for more sustainable materials for their products. Sometimes this means going with a bio-based material. Sometimes this means going with a recycled option. But often it can be going with a resin or material that might have a lower environmental impact, possibly a lower carbon footprint. And that leads us to discuss a possible solution: aliphatic polyketone, abbreviated PK. Now, this isn't necessarily a brand new material. And polyketone was originally developed by Shell as Carolon in the early 1990s. And when Shell launched this material, it was expected to compete with acetal, abbreviated POM, PBT, and nylons. Now, Shell wound up exiting the polymer manufacturing game before polyketone could be fully commercialized and introduced and taken up into the market. Recently, the material has been brought back onto the market and is available in a variety of product grades well suited for demanding applications. Another great thing about polyketone is it's an eco-conscious engineering resin. And I'll talk a little bit more about this later, but the polymer structure itself is made primarily from carbon monoxide and ethylene with a little bit of polypropylene in the backbone. This makes the material semi-crystalline. It's this alternating copolymer of these two monomers. And in terms of material properties, it has good tensile, flex, thermal, and impact properties like nylons, while having excellent lubricity and wear, chemical resistance, and dimensional stability like an acetal. So it fits between these two types of polymer families in terms of its properties. Again, being semicrystalline, it's also going to have a similar type of shrink as a nylon or an acetal, which makes it useful for those types of applications. Now, I'm a polymer chemist by training, so I love throwing structures into webinars to show how the material properties of a resin can really be tied back to the structure. But you don't have to be a polymer chemist to understand these structures to understand the similarities. So polyketone on the bottom is very similar structurally to a nylon 6,6 and a nylon 6,6. These are all semicrystalline materials that contain carbon-oxygen carbonyl functional groups. And those are the structures that are going to be shown in the red circles. Those are the oxygen atoms. However, polyketone noticeably lacks the backbone nitrogen present in the nylon amide bond. That's shown in the blue NH functional groups on the nylon 6 and nylon 6,6. And this makes polyketone much less hygroscopic than nylon 6 or 6,6. And as a result, the material properties are much less sensitive to moisture conditioning. Another interesting thing to note about polyketone is it's not a perfectly alternating copolymer of carbon monoxide and ethylene. If you actually have a perfectly alternating copolymer of those two monomers, the material is so highly crystalline that it becomes very difficult to process and use. So as a result, there's a tiny bit of polypropylene that is copolymerized into the material as a sort of engineering defect that winds up improving the processability. It's one of the unique features of polyketone. This makes the material much more moldable, and Jeremy's going to talk a little bit about that later in the presentation. So polyketone has a very low carbon footprint compared to many other engineering thermoplastics, in particular nylon 6,6, nylon 6, and acetal. Compared to nylon 6,6, this is a 61% reduction in carbon dioxide, according to a third-party life cycle analysis. And this is primarily due to the low carbon footprint of the monomers, right? We're talking about carbon monoxide and ethylene and maybe a little bit of polypropylene. And this is going to be more similar to that of a traditional polyolefin. The take-home message here being, with polyketone, you're going to get engineered thermoplastic performance with a polyolefin type carbon footprint. So for the rest of the presentation, I'm going to be talking a little bit more about polyketone and comparing against nylon, particularly against glass-filled nylons. And this is going to be due to that similarity in structure. And we've talked a little bit about nylon 6 and nylon 6,6 to this point, but polyketone is also a really attractive replacement for more specialty long chain, low moisture nylons. Things like your nylon 12, your nylon 11, nylon 610, nylon 612. In this case, what we're showing on this graph is spider charts of relative polymer properties of glass-filled resins compared to polyketone. And polyketone is going to be shown in that nice green turquoise color. Now, I'm not trying to say that polyketone is the excellent performer in every single aspect of physical, mechanical, and impact properties. But what it does give you is another tool in your product development toolbox. And it really depends on which properties are most important for your specific application. And what we've seen a lot at Avient is customers that are frustrated that they can't get nylons for their current application where they might be over-engineered for that current application. And so polyketone then becomes an important consideration where it might perform even better than the customer needs for that application. However, there can be some trade-offs. So for example, polyketone compared to nylon 6,6 has a higher density. So you're going to have a slightly heavier part. It also has a slightly lower maximum continuous use temperature. So if you really need the high performance temperature of a nylon 6,6, polyketone might not be the best choice. Another factor to consider when comparing against these broad family of nylons is going to be the cost in use. So I already mentioned that polyketone resin is a little bit more dense than traditional nylons. It comes in at 1.24 grams per cubic centimeter, whereas your nylon 6 and 6,6 are probably closer to 1.1, 1.15. and your long chain specialty nylons are probably closer to 1. However, polyketone has a similar or better heat performance than those long chain specialty nylons at a lower cost. So you can wind up having a material that will satisfy your performance requirements at that lower cost. And again, these are all just relative price indicators. These dots might have shifted around since we made this graph up a few months ago. So it's something to consider when you're looking at developing with polyketone. I've been talking a little bit earlier about the moisture factor because this is one of the things that really interests me as a polymer scientist, that difference in moisture uptake, because it can be a significant drawback to using a nylon 6 and 6/6. Specialty long chain low moisture nylons like nylon 612 and nylon 12 are often used in applications that cannot tolerate property change with ambient moisture conditioning. These might be applications that include electrical parts or shooting sports type applications. Now, these type of nylons have these lower moisture uptake due to that longer carbon chain in their backbone that makes the materials more hydrophobic. And you can see the relative properties of moisture uptake in the graph on the left. Here we're looking at unfilled resin that is looking at equilibrium moisture. So it's 50% relative humidity. And in this case, basically a higher bar indicates the material is taking up more moisture. Unsurprisingly, nylon 6 and 6/6 take up quite a lot of moisture, and you see that in the resultant properties, whereas these long chain nylons take up less moisture, and polyketone actually takes up the lowest at 0.5%. There's also going to be a noticeable difference in the moisture uptake behavior of polyketone when you add in typical reinforcements and additives, in this case, 30 weight% short glass fiber. And we're showing this as a rapid moisture aging study on the graph on the right. In this case, we're taking samples and aging them at 62% relative humidity, 70 degrees Celsius, over a period of 500 hours. Again, a higher data point here indicates more moisture being taken up. And so what you see is polyketone does take up some moisture, but it plateaus relatively quickly and remains pretty steady throughout the duration of the experiment, whereas glass-filled nylon 6 and 6/6 show a burst of moisture uptake, and it kind of tends to increase throughout the experiment lifetime, eventually peaking at about 400 hours. So again, take-home message here being that polyketone takes up much less moisture even under extreme conditions. And this moisture uptake is important for how it changes the physical properties. And what we're going to be talking about on this slide is the property retention of polyketone compared to nylon 6 and 6/6 when you're looking at samples that are dry as molded versus conditioned. And this can be important because you might look at a technical data sheet and see properties for a nylon or nylon 6/6, and it's one thing to see a property when it's dry as molded, but when you understand that moisture is going to affect those properties, you want to understand how it's going to affect your ultimate part performance. So it'd be good if you only had to measure those properties once, or you could trust that your dry as molded data is going to be indicative of your performance. And so in this graph, I know there's a lot of bars, a lot of properties located at the bottom, but we're talking about property retention. So that dotted red line means 100% property retention if we're looking at a dry as molded sample compared to an equilibrium moisture conditioned sample. So if a bar is near 100% on this graph, it means that the property doesn't change all that much. And what you see broadly in this graph is that glass-filled aliphatic polyketone does not change its properties all that much when you're comparing dry as molded to moisture conditioned, whereas nylon 6 and 6/6 do noticeably change. In terms of your flex properties, your tensile properties, they primarily drop off, with the exception of tensile elongation increases a little bit. It's interesting to note the notched IZOD impact actually improves a lot for glass-filled nylons. And this is because water actually plasticizes nylons and makes them more impact resistant. So this can be a benefit for things like nylon 6 and 6/6. But ultimately, what we're trying to tell you here is that polyketone is going to have similar properties, dry as molded, as it will have in its final end use. Let's talk a little bit about specialty nylons. In this case, we're not doing a dry as molded to moisture conditioning compare. we are just comparing the properties of glass-filled polyketone to that of 3 different grades of specialty nylons, nylon 12, nylon 610, and nylon 612, all loaded with 20 weight % glass fiber. And so here, the dashed line at 100% represents the properties of polyketone, and then we're looking at how do these properties of the specialty nylons compare. And what you really notice in this graph is a lot of the properties seem to match that bar near 100%. There is a little bit of a difference for the glass-filled nylon 12 for impact rating, but broadly, there are good similarities and good agreements between all of these samples. And so the take-home message here is that polyketone can be a solution, a replacement for applications that are well suited to specialty nylons, especially when you consider the advantages in sustainability and cost in use. Now, one of the questions that comes up a lot with polyketones is the thermal performance and the thermal comparison, because we're talking about nylon 6 and 6,6. And I already mentioned that polyketone doesn't have the same thermal performance as a nylon 6,6, the same max continuous use temperature. And there's a number of ways to test this. Now, a lot of people will use heat deflection temperature as an indication of thermal performance, but that doesn't really give you a good analytical type understanding of how a material fails and where the upper critical max continuous use temperature will be for a resin. So in this slide, what we're looking at is a dynamic mechanical analysis, or DMA. And this is used to show the relative max continuous use temperature of polyketone compared to nylon 6 and 6,6. Again, we're talking about glass-filled samples here, in this case, 30% short glass. Now, the DMA curve here is going to help us get a clear picture of how the properties change with temperature, and that's going to influence our ability to recommend a material for a specific application. In this case, we're measuring the elastic modulus change with increasing temperature. And I don't expect everybody on the webinar to be an expert in polymer rheology, but the important thing to note here is the shape of these curves and looking at the slope. And once the slope begins to change, what that tells us is that the material properties are changing to a noticeable degree and that we're in a region above the ideal use temperature of the material. And so when you're comparing polyketone to nylon 6 to nylon 6,6 in these graphs, what you see is that the material curves for nylon 6 and polyketone are very similar. They start to change their slope at around the same region, whereas nylon 6,6 has a relatively linear slope throughout the entire tested range, even above 210 degrees Celsius. So what this tells us is probably a good rule of thumb is that polyketone max continuous use temperature is probably more likely similar to a nylon 6 than a 6,6, especially when we are reinforcing the material with glass fiber. If we're talking about unreinforced resin, the max continuous use temperature of polyketone is probably somewhere around 105 to 110, although there are certain things we can do with different additive and stabilizer packages to move that up a little bit, similar to that of nylons. And one of the great benefits of using polyketone is its enhanced chemical resistance compared to nylons. This is seen in this slide demonstrated against 30% sulfuric acid. And we're just taking tensile bars and dropping them in and doing some simple soak tests. Now, glass-filled nylon 6 and 6,6 test bars dissolved within 1 day of this experiment, while the polyketone samples remained stable after 20 days. These images really show you a stark visual representation of the excellent chemical resistance of polyketone. But we have also soak tested performance against other chemicals, and that includes hydrochloric acid, calcium chloride, antifreeze, ammonium hydroxide, bleach, and ethanol. And in each case, the polyketone physical property retention is superior to that of nylon 6 and 6,6, further confirming the excellent chemical resistance. And I'm not trying to say that the chemical resistance of nylon 6 and 6,6 are bad. It's just that nylon or polyketone is slightly better under these test conditions. So if you have an application where chemical resistance is absolutely critical, polyketone is an excellent material to consider. Another slide looking at the long-term chemical resistance, in this case, 40% glass-filled material, 30% again, looking at nylon 6 and 6,6, but testing against water ethylene glycol mixtures. That's another name for antifreeze. And again, looking at long-term 1,000-hour data at 120 degrees Celsius, 248 degrees Fahrenheit. Again, polyketone chemical resistance is excellent even at these elevated temperatures. The glass-filled samples show better property retention and lower dimensional change as compared to these two resins. Let me talk a little bit briefly about the wear and friction resistance of polyketone. So the material is highly crystalline, and highly crystalline materials often are selected for applications where wear resistance is crucial. And this is shown in the graph on the left, where we're doing a standard ASTM thrust washer wear test of unfilled resin, in this case nylon 6,6, acetal, and polyketone. And this test occurs over 2 weeks, where you're measuring the wear resistance of a material under a certain speed and certain weight. And as that material wears down, basically these bars grow. So a larger bar in this graph indicates worse wear performance. And what you see is polyketone has the best wear performance, especially against acetal, especially compared to acetal, which is often highlighted as one of the most wear resistant unfilled thermoplastics. Additionally, additives like Teflon and silicone can be added to polyketone to reduce the coefficient of friction, similar to what you would expect to other wear-resistant low-friction thermoplastics like acetal and nylons. So this makes polyketone attractive for applications in which wear resistance or low friction are crucial. These could be things like bearings, gears, slides, and conveyor belts. And that's shown again in the graph on the right. Now, up to this point, we've been mainly discussing polyketone base resin and glass reinforced base resin against nylon. But I also want to mention the versatility of polyketone for many other specialized applications. The material can be blended with other resins. It can be blended with other common thermoplastic additives like flame retardants and UV stabilizers. And you can also formulate it into specialty high impact grades. We've recently developed a number of these high impact grades that are able to go head to head against an industry standard high impact nylon 6,6 type materials. This is a similar graph as we showed earlier, where we're comparing property difference of polyketone to a high impact nylon 6,6. And what you see is generally good agreement in physical and mechanical and impact properties. And so with that, I'm going to turn the reins of the presentation over to Jeremy to talk a little bit more about the applications and molding of polyketone.
Yeah, good morning and welcome everybody. So my name is Jeremy Gray. I'm going to kind of pull us back to reality a little bit, get away from some of the graphs and go over some of the details around polyketone and really answer some questions around what is the material, how is it going to perform, and what do I need to do in my application personally to use this material successfully. So really what I do is my role is application development and tech service. The application development side of things is really working on really what you see on the screen for this slide. And my description kind of bleeds into some of the questions that are going to get answered here. I work on part design, tool design, working with mold flow analysis, FEA as well. Now, when looking at polyketone as a new material coming into applications, there are obviously going to be some challenges. The 3 points that you see on the screen are really where I would like to focus today. So the number one question that anyone is really going to ask is mold shrink. How does this material compare? Especially if we're looking at a nylon replacement, mold shrink is going to be the largest question and the biggest hurdle that people are going to face with existing tooling, trying to replace that as well. And then going into the processability, really, how does this material fare in molding, and really what do I need to do to be successful? And then the colorability side of things. How far have we pushed this space? What can we do with polyketone? What kind of pre-colored solutions can we hit? So going into the mold shrink side of the material and kind of answering some of those questions, There's a lot to digest on this slide, but really what I would like to focus on first is the image on the left side of the screen. This was an in-house study that we had recently done with our polyketone solutions within Moldflow. So what we did here was we ran a simulation based off of our ideal molding simulation results based off of polyketone. And then we did the same thing with one of our glass reinforced nylons. Now, the plot that you see on the screen is the post-mold shrinkage, known as warpage in Moldflow in the X, Y, and Z direction. And what we did was we overlaid these two plots and then plotted the differences between the two. So when people ask the question, what is the mold shrink difference between polyketone and that of a glass-filled nylon? What you see on the screen is really a representation of how close the shrink values of polyketone are to that of nylon. The red to green is the material pulling away from center, and then the purple to kind of darkish blue is the material pulling in on itself. So the areas to kind of focus on are the red and the purple. Those are the areas where you see the most difference between polyketone and nylon. But then again, if you're looking at the actual values and the magnitude of the shrink, the differences are pretty insignificant. So in general, this is a great tool to kind of show the uniqueness of a material, how it's going to shrink with that thicker region in the center, as well as, you know, showing something that's a little bit more exciting than a tensile bar or a plaque when looking at the mold shrink and how a material is really going to react post-molding. So getting into the processing, this is really how I like to split out processing as a whole, because in general, when you say processing, it's typically, you know, a lot kind of encompassed under one umbrella. So I like to split it up into three sections. I consider that drying, processing, and then post-molding behavior. Another way that you can look at it and kind of think about it is that you have the pre-processing, which is the drying, anything that you need to do before actually processing the material. And then you have the actual processing, which is the actual process of you know, producing the material and pushing it through your extruder or injection molding machine. And then you have your post-process. What do I need to do to these parts to keep the dimensional stability? What do I need to do to you know, assemble with other components or any kind of secondary operations? So that's how I like to process it and kind of move this along. When talking about drying, there's really no need to dry the material. It is not required, but it can be recommended for some of our solutions. And this is actually a positive for the material, because a lot of molders and suppliers tend to have issues with drying materials, as well as it just adds another factor into the mix. When you have to dry a material, you typically have to hit a certain threshold, or you get some kind of issues via processing. So having a material that is not necessarily going to pick up any moisture from ambient temperature and ambient environments is typically a benefit, and it helps to ease that process of getting the material through. So now talking through the actual process of the material, how does this material perform? How does it handle? How does it compare to that of nylon solutions? The way that I like to put this is that polyketone typically performs better and is easier to process than nylon. It is not as sensitive in terms of the viscosity of the material causing you issues. The material has great flowability, great compressibility in the cavity. The only issue that we tend to call a negative, but it's not necessarily negative, you can see this with all materials, is that it is generally less thermally stable in a molten state when compared to other materials that you more commonly would use. And what that means is that while processing, you tend to want to stay away from long residence times. Anything over an hour is not recommended, but that's kind of the case with most materials. Other than that, the material is very robust and will be a great offset for nylon in terms of what you're used to in processing. You're not going to see any kind of changes really in pressures, and the material should process fairly well. Now going on to the latter part of that, okay, now the parts have been molded. What do I need to do post-molding to be able to keep this part where I want to keep it in terms of dimensional stability? Polyketone will have very little shift in properties when you compare it to nylons. That's kind of the known fact and known Achilles heel of nylons, is that the material will tend to shift post-molding, and that's why you see dry as molded versus conditioned settings on a data sheet with nylon. With polyketone, that is not the case. You don't need to condition the samples. What you get out of the press is what you will see 10 hours from now, 15 hours from now, 500 hours from now. There needs to be no annealing, anything of those sorts. The material is really conditioned in a sense that it is very low moisture, as John had stated. It's a great material for that kind of application. So what you get out of the press is what you will get, like I said, 500 plus hours from now. And again, kind of going back to the drying, this is a good thing for a lot of our customers who use this material that don't want to take up the space on their shop floor for secondary operation machinery, whether that's an oven for annealing. Polyketone kind of eases that process and just allows you to do what you need to do with an injection molding machine and not have to worry about anything that would happen before or after processing. So going a little bit into the color technology, John just rambled on for about 20 to 30 minutes, but did not mention how unattractive the natural state of the material actually is. So the image that you see on the far left, kind of the earthy tone brown color, is what polyketone looks like in its natural state. The image that you see on the far right is a lot of the work that we've done internally to create pre-colored solutions for polyketone. The image on the right is not a stock marketing image that we just kind of pulled for the presentation. These are actual color targets that we have hit and that we've actually worked on for some of our customers. We plan to expand this portfolio a little bit more and work towards getting other special effects, colors, and kind of recipes for that as well. But what you see on the screen is really what we've done so far. And we have a little bit more information online to kind of show what we've done with our technology. Now, this last slide that I'm going to go over is kind of the catch-all for polyketone. So if there's anything that you would take away from my portion of the presentation and what I've done so far is to take this slide and kind of review it and understand really what polyketone is. I think it's a great slide that kind of gives a summarization of what the material is. It has great dimensional stability, great chemical resistance, and wear resistance. We've seen a ton of interest with polyketone in replacing nylons in automotive, consumer, industrial, electrical, for various housings, enclosures. And I did see a question about healthcare. I believe that's where we had started this material. So healthcare is a section that we've kind of pushed polyketone to get into. Typically, and there's one more portion that I want to go over for this, nylons are over-engineered for a lot of the solutions that they're in. Polyketone would work just fine. The only issue is the temperature requirement. So polyketone typically falls between nylon 6.6 and 6 in terms of temperature. So if you have an application where you're going to see high temperatures, a lot of customers will tend to lean towards nylon 6.6 for its high temperature requirements. And then if you have an application where a material is not necessarily in need of high temperature, people will tend to lean towards nylon 6. So polyketone kind of falls in between these two products in terms of where its temperature requirements kind of lie. So that gives you an idea of where the material kind of fits and how it will work. So on the next slide, John is going to get into a little bit more detail with polyketone, some of our other offerings, as well as some of the sustainability that we've done with the materials.
Thank you, Jeremy. So starting to wrap things up here, we've been primarily talking about polyketone in this webinar. And that's because we feel that it's a very good answer to both sustainability questions and concerns about nylon availability. But at Avient, we have many different alternatives to nylons and many more sustainable offerings to help our customers be sustainable. So even if polyketone is not the right resin for your specific application, we have a number of different answers to these type of questions, and more information can be found on our website. So with that, I'd like to begin to wrap things up and to bring us back to a summary of what we've talked about today. Started off by talking about the market drivers and highlighting that the nylon supply is cyclical, and polyketone can be a high performance alternative with a more stable supply and a lower carbon footprint over the product life cycle. Polyketone based formulations perform well against nylons and acetals while providing excellent chemical resistance, low moisture uptake, and wear resistance. Polyketone formulations can be customized with common fillers, impact modifiers, and additives to enhance the performance for specific applications. And Avient's application and development team are available to evaluate your application's suitability for polyketone with our grades of materials. So with that, I would like to thank everybody for their attention. Thank you for coming today, and we'll begin to wrap things up and begin to answer questions that you have for us.
Thank you, John. And we'll get started with the Q&A session here. We've had a few questions come in about will the slides be available and this recording? Yes, to both. You will be receiving an email that will have the slides as well as this recording, so you'll be able to watch this again. With that, our first question is for Jeremy. Is there a drop-in replacement for nylon?
Yeah, so it depends on what you say when you say nylon. I mean, a lot of solutions for nylons are glass reinforced. So we have unfilled as well as glass reinforced filled solutions of polyketone. So we have a lot to offer. So I guess to answer that question generally, yes, we have solutions that can be used as drop-in replacements for nylons.
Thank you. The next question is for John. Does it include formaldehyde?
No, so there's no formaldehyde added to polyketone, but usually where this is more of a concern is for acetal type applications. So when acetal degrades, it releases formaldehyde. And so that can be a concern for a number of different types of applications, or just for processing. You know, if you overprocess a resin and release formaldehyde, that's not good for anybody on your team. So an advantage of polyketone compared to acetal is that there's simply no concern with toxic off-gassing like that. There's no concern of degradation into harmful formaldehyde gas. So it's definitely an advantage of the resin comparing to acetal.
Thank you. The next question is for Jeremy. What are the operating temperature ranges?
Yeah, so operating with polyketone, again, it depends on the type of fillers in there. But the general range of operation in terms of Fahrenheit is anywhere from 430 up to, I say 480, but you can go to 500 depending on your barrel, the size of the barrel, the size of the shot, how much it's taking up of the barrel. So anywhere from 430 to 500 Fahrenheit is typically the operating temperatures that we like to see with polyketone.
Thank you. The next question is also for you. How moisture sensitive is it in the final molded state?
Yeah, so I can touch on this briefly, but John, I think I want you to kind of step in here because I know you've done a lot of work with polyketone, but obviously it's going to pick up a little bit less moisture than nylon, but I know we've done some studies on some final parts just to kind of see how the material actually does fare. So John, I'll leave that one for you.
Yeah, so I've seen a few questions come in related to water content, so I'm going to try to answer a few of those when we're talking about this. So final water contact, generally the materials that we've seen test very well. And, if you start to raise the temperature above that 100 degrees, 120 degrees Celsius, you're going to start to notice probably some property decrease over time, depending on how we formulate it. Generally, at high temperatures over long periods of time, polyketone can tend to discolor, but that's if you keep the material, near that maximum continuous use temperature for long periods of time. But if you're within a more ambient or slightly elevated temperature range, polyketone is excellent for water contact, and it's actually something that can be highlighted as a special application for polyketone because the base resin itself, there's a number of grades, including medical certified grades, water contact certified grades. So you can use polyketone for things such as water pumps, water storage tanks, things like that, and see good performance over time.
Thank you. The next question is for John. Are there sourcing concerns for this material?
So I'll preface this by saying I'm more of a polymer scientist than a sourcing specialist, but everybody's experiencing sourcing issues right now. The great thing about Polyketone is we work with an excellent supplier. We source and stock the material, locally to our manufacturing sites. But it is always helpful to have more information about specific applications and to try to forecast out orders and information as long as possible so we can ensure that there's no hiccups when we're developing a material for a customer.
Thank you. The next question is for Jeremy. Can they be used for medical application and are tested for biocompatibility?
Yeah, I touched on this really briefly because I saw this question while I was presenting. When we had first developed Polyketone, the actual first few commercial grades that we developed were for the medical field, replacing PCABS. So to answer that question, yes, we have solutions in the medical field, and that's actually kind of where we started, and that's where we have the most solutions currently.
Thank you. The next question is also for you. How is the appearance of a glass-filled PK versus glass-filled nylon 6 and 6.6?
Yeah, this is actually a really good question. A lot of that has to do with the processing, but just kind of talking on the materials and keeping the processing aside, Polyketone kind of fares between the two materials. Nylon 6.6 that is glass-filled tends to have a grainy kind of look to it, whereas nylon 6 is more of it fills in the color more. So it's kind of in the middle. If it is in its natural state, Polyketone, you will see some of those fibers on the surface. But if you start to get some of the pre-colored solutions that I showed in my slides, the reds, the blues, the greens that kind of hide that, it looks more of a nylon 6 where you get kind of like a darker piano color. So it's kind of in the middle. But then again, it really determines or is determined by how you're processing. So the mold temperature and kind of your capability with processing will also determine the surface appearance of the material.
Thank you. The next question is also for you. Does PK need desiccant drying before molding like PC does?
No. So polycarbonate, like other materials, is known to be a challenge to dry, and it's really sensitive and needs to be kept within a certain range for drying. Polyketone is not necessarily like that. You can dry the material just for kind of like good practice, but it does not need to be dried. A specific dryer is not needed, so a desiccant versus any kind of conventional oven dryer or anything of that sort can be used. In some scenarios, the drying is not necessarily for the resin, it's for some of the fillers. So if we have a polyketone that has a flame retardant that could potentially pick up moisture, that would be a scenario in which we would recommend drying. But in general, for the base resin, there's no specific requirements for drying.
Thank you. The next question is for John. Why is HDT not a good indicator of thermal stability or heat resistance in comparison with DMA measurement?
So I like the HDT test as a quick way to compare thermal performance between materials that are very similar. So in this presentation, we talked a lot about 20 and 30% glass filled nylon 6 and 6.6 and polyketone. And if you look at the data sheets, what you'll see is the HDT values for nylon 6 and polyketone are very similar, and nylon 6.6 is a little bit higher. But it just gives you one data point. And when you think about how that test works, you're taking a flex bar, so a little rectangular bit of plastic, then you're putting it under a certain amount of pressure, and then you're just heating it up, and you're measuring the temperature at which that bar starts to sag. And there's very few applications in which plastic finds itself that's the overall method that you determine part failure, right? The material physically melts into forms and can no longer be used. And so HDT gives you a good indicator, but it's usually going to be high, and it's going to be higher than your max continuous use temperature. And so in that case, DMA gives us a little bit more information to show really where do we see that property begin to drop off. And in that case, it is all application dependent, right? But it gives us more of an idea of if a customer comes to us and says, I have a part that is going to undergo a temperature of this degrees Celsius or this degrees Fahrenheit, is that above or below what you would feel comfortable with based on using any of your developmental grades? Because we're not going and getting RTI certifications for every single experimental and developmental grade, but DMA allows us to get a lot more information than just a simple HDT test to understand, what are we doing to the thermal properties as we make up not only our commercial formulations, but our customer specific formulations.
Thank you. The next question is for you as well. Can PK be reinforced by carbon fibers as well?
Yes, although I don't believe we have any commercialized formulations with carbon fibers yet. It is possible to reinforce polyketone with carbon fibers.
Thank you. The next question is for Jeremy. Are polyketones available in halogen-free flame retardant grades? What is the highest achievable UL94 rating?
So this is something that is, and I want to say fairly new for us. We've started working on some of our flame retardant grades. We know that a lot of customers want non-hal as their solution for FR. So we have solutions that we're working on, both halogen and non-halogenated. Depending on the flame performance, part of that question was asking, how good can we get the material to be? That depends on the part geometry, but we can hit V0 at select thicknesses. It just really depends. So there's really no limitation. We do have solutions in non-halogen versus halogenated.
Thank you. The next question is for John. How is PK priced in comparison to the nylon 6 and 6.6?
This is a question that comes up a lot as well when we do polyketone replacements and start looking at different opportunities. Now, I should mention, again, I'm less of a pricing expert than I am a polymer scientist, but I would say generally, polyketone resin falls closer in price to nylon 6 and 6.6 than it does many of those specialty nylons. And it really depends on not only where you are globally, but also what your source of nylon is. Is it prime? Is it post-consumer, post-industrial? And what are the additives being included? Oftentimes, if a material is over-engineered, maybe we can come up with a nylon or a polyketone material that contains a different additive package that can provide more value. And it also changes with that market cycle. I've seen points too where polyketone becomes much more beneficial in a value standpoint over the past few years than it was when it might have been introduced 25 years ago.
Thank you. The next question is for Jeremy. Is polyketone compliant for food contact repeat use products for both FDA and EU, specifically with milk?
Yeah, we have solutions that are NSF 61, which I believe is just water. I don't necessarily know how much further we've gone than that with FDA. John, I don't know if you have anything from that standpoint, just from a formulation side, but I know a majority of our solutions have NSF, well, not a majority, but some of our solutions can do NSF 61, which, a lot of polyketone is going to be around water. So that's something that we kind of focused on.
We can make solutions FDA with FDA approved raw materials. It just depends on the application. So we've made those both with reinforced, both with blended grades. We didn't get too into all of the commercial grades that we have, but that is an option for our materials.
Thank you. And the next question is for Jeremy. Considering the shrinkage difference, could you reuse an existing PA66 mold to shoot PK, considering equivalent glass levels, say at 30% GF?
Yeah, so the closer the glass levels, the easier that it will be to kind of match, and that's a lot of what we do in house. So we have a lot of unique geometry that we mold, and a lot of that is cut for 30% glass filled nylon 6/6. So when we went through and did all of our studies with Polyketone, we did not have to make any changes to those molds. We didn't have any issues with parts sticking. Material molded fine. That's typically, what we see in application is a lot of people are replacing nylons with these Polyketone materials. And if you keep the glass loading somewhat equivalent, you are pretty successful with that.
Thank you. The next question is also for you. Have you had an issue of cross-linking in compounding or injection molding with PK and its compounds?
So we've had some issues where we've gone a little bit too hot, and I think the next question is talking about the temperature requirements, so I can kind of cover both of these here. At what threshold temperature will PKE begin to cross-link? We tend to say, like I said earlier, 500 Fahrenheit, and that's mainly with hesitancy around how long someone will have a material in the barrel. We've had issues with customers leaving material in for hot runners, and that's not necessarily an issue on their end. It was an issue with the hot runner, where there were kind of stagnant regions where the material was kind of building up, and it was just poor kind of design from the hot runner company. The material kind of sat up and sat there for a while, and obviously overcooked and started to cross-link. It's hard to say at what temperature that starts to happen, because it's typically a larger dependent of time. So anything, if you're running under 500 degrees Fahrenheit where you're pushing the material through, anything under an hour, the material is robust. But I would hate to give one specific temperature, because there's a lot of other factors that go into that.
Thank you. The next question is also for you. How does the as molded surface roughness of Polyketone compare to nylons?
Yeah, that's a large factor in the mold surface of the actual mold. So if you have a textured surface versus, say, like a Class A finished surface, if you're talking about unfilled, it's I would say that it's similar to both materials. But if you have a filled solution, like I said earlier in one of the other questions, it's going to be similar to more similar to nylon 6/6, where you kind of have a little bit of a rougher surface, but there's other things that we can add into the process or into the formulation to kind of get away from that. I guess you can go into the next question, because it kind of adds on to what I was about to say next.
Okay, perfect. So the next question is, visual quality PK compares to PA6/PA66. I mean, visual quality of the surface, can it be visual component for home appliance products with texture or high gloss?
Yeah, so we just recently developed a new product line based around nylon 6 that is kind of for these applications. That's a high gloss, extreme kind of panels or any kind of high visual parts. And like I said, we did this for nylon 6. After we've seen a lot of that success, we've been looking to kind of get into that with Polyketone, just as a second source or kind of a second solution for customers. So that, yes, that is something that we've been looking to get into, and we're kind of in the process of developing solutions for it. So as of right now, I don't know how much we have, but I know that's something we're working on.
Thank you. The next question is also for you. Is there any change in mechanical properties with color addition?
Yeah, so it's what you would see with any other kind of material. When you think about adding color to a formulation, you're adding a contaminant to the solution. So typically what we see with polyketones is what you would see with any nylons, nylon 6 or 6/6. If you're adding a black, obviously you're going to get a slight degradation of your properties. If you're adding a color that's a little bit more challenging to hit and requires a lot more kind of filler. So it's commonly known that when you're hitting a white, you're going to lose a lot of your properties, because getting from your natural colored resin to a white is pretty challenging and takes a lot of filler, which again is a contaminant. So it's going to be similar to what we've seen with other materials where, yes, if you're trying to hit these difficult to reach colors, you will see a change in your mechanical properties.
Thank you. This next question is also for you. Can the materials be colored with conventional color feeders, or does it have to be ordered pre-colored?
It can be pre-colored as well as using a color concentrate at the press, so we can supply the material in a natural state, and then whether liquid color or color concentrate is used, those are always options.
Thank you. The next question is also for you. Are UL yellow cards available for standard grade offerings?
I want to leave this question for John. I'm not sure what he's done with UL. I know that that's something we want to get into.
I'm trying to think of how many grades that we have commercially launched, because we also have internal flame capability testing. So we have a number of grades that we have tested to be UL 94HB, a number that have been tested to UL 94V0. In terms of getting the yellow card, I think there may be some specific grades, particularly on the healthcare side, that we might have yellow cards for, but I would need to check. If it's a requirement, we can definitely do that. I'd say more often it's on a per application and per customer basis.
Thank you. The next question is for Jeremy. Is this material mechanable? Is this material available in sheets 4x8?
Yeah, so the material is machinable. It's not, and I'm trying to think of the word here. It's not abrasive enough where machining is going to be an issue. So yes, it can be machined. But is it available in sheets? We haven't done much with extruding sheets of the material. As of right now, majority of what we have done is in injection molding, and I believe we have a few solutions that we're working on for extrusion. I don't know the melt strength of the material in that sense to know if it can be extruded into a thin sheet, but we are getting into extrusion. It was just, injection molding is kind of our number one priority. So we kind of focused on that first, but like I said, extrusion is kind of the next step that we're looking at.
Thank you. The next question is also for you. How good is the behave of PK in applications in contact with drinking water? Do you have data of KTW conformity at 60 degrees Celsius?
Yeah, so I touched briefly. We do have solutions that are NSF 61. I think John had mentioned this a little bit in his portion of the presentation, but where kind of Polyketone tends to excel is in high water applications. So any kind of pump housings, components where the material is going to basically be sitting in water for an excess period of time. So we do have solutions that the fillers or the parts of the formulation are NSF 61. I don't know, and I'm unaware of the KTW kind of requirement. I took a note of that, and I'll look a little bit more into that, but I don't know, John, if you have anything on that.
I don't, I'm sorry.
Thank you. The next question is also for Jeremy. Is there any experience in two-component molding / bonding of TPE or EPDM on PK?
Yeah, it's good that question actually came up. So the one slide that I had showed on the mold shrink that had the connector rod, which was the component that kind of looked like a thin rod that had two holes in it. That tool actually has the ability to be two-shot, gating on one side and gating on the other. And we've actually done a lot of studies on gating polyketone and two-shot with other solutions, so with nylons and with some of our TPE solutions. So that is an option. I don't have specific grades which I can kind of give right now, but we have played around with that, and we've done the work within our labs.
So Jeremy, I really want to jump in just real quick, because I believe we also recently launched some TPE grades specifically for overmolding onto polyketone recently.
Thank you. The next question is for Jeremy. Would you recommend PK as a replacement for POM and insulin pin-ups?
So I'm not super, I guess, involved in knowing why POM would be selected for that application. But John did touch briefly on this, is polyketone is naturally is a natural lubricant. It performs very well compared to POM, so it has very similar properties in that sense. So if that's the reason why POM is being used for that application, I would say yes. But if there's another reason why POM is being used, I wouldn't be sure about that.
And this will be our last question for today, and it's for John. How is the fire behavior of PK?
So if you're looking strictly at the base resin, polyketone, it's like many other thermoplastics. It's probably similar to a nylon 6 or 6.6, maybe a little bit of improvement there. It forms kind of a nice char layer. But in general, if your application requires some sort of flame retardant rating or performance, we'll typically add in a number of standard flame retardants to meet that requirement.
Thank you, and I would like to thank everyone for attending today's webinar. Just as a reminder, we will be sending you a link to the recording of today's webinar so you can watch it anytime and share it with others at your company. We will also follow up to any questions we weren't able to get to today. Now you will be redirected to Avient's website for more information. Thank you again for attending and have a great day.